Have you ever gazed up at the night sky, letting your mind wander among the stars and wondered if we are truly alone in this vast universe? The darkness above us is filled with countless points of light, each one a sun, each one a potential cradle for life. For millennia, this question has inspired our greatest stories, our deepest curiosities, and even our earliest attempts to understand the cosmos. From ancient cave paintings to the earliest manuscripts, humanity has always looked upward, searching for meaning in the stars. Now, for the first time in history, science is moving this question from the realm of philosophy and speculation into the world of observable, testable reality. Researchers and scientists are no longer just dreamers, they are explorers, using powerful tools to seek real answers. The universe is unimaginably vast, filled with billions of stars and planets. The ingredients for life, water, carbon, energy, seem to be scattered everywhere. With every new discovery, the possibility that life exists elsewhere grows more tantalizing. Yet despite all this potential, the cosmos has remained silent. No messages, no signals, just the quiet hum of the universe, until now. Today, August 5th, 2025, that silence may have been broken. A faint, mysterious signal has reached us from a world hundreds of light years away, sparking excitement and cautious hope among scientists everywhere. The James Webb Space Telescope, humanity's most advanced eye in the sky, has detected a chemical signature in the atmosphere of a distant planet, one that, on Earth, is only produced by living organisms. This isn't a direct encounter with aliens, but it's a subtle, profound clue, a molecule that could rewrite our understanding of life's place in the universe. It's a whisper from across the stars, hinting at possibilities we've only dreamed of. The search for extraterrestrial life is a meticulous process, built on skepticism, careful analysis, and the relentless pursuit of truth. Every discovery is scrutinized, every anomaly investigated. The announcement of a potential biosignature is just the beginning of a rigorous scientific journey. It's a call to the global scientific community to investigate, to question, and to verify. Every alternative explanation must be exhausted before we can seriously consider life as the cause. Scientists will debate, test and retest, searching for any other possible source for this signal. In this story, we'll explore the discovery itself, the telescope that made it possible, the distant world K218b, orbiting a cool dwarf star far from our own solar system, and the molecule at the heart of the excitement, dimethyl sulfide, a compound that on Earth is only produced by life in the oceans. We'll examine the evidence, the data, and the scientific reasoning that makes this finding so compelling, and why it has captured the imagination of people around the world. This is a story about data, about photons that have traveled for centuries across the emptiness of space to reach us, carrying secrets from a distant, water-covered world. What might they reveal about our place in the universe and about the possibility that we are not alone? To truly grasp the magnitude of this discovery, we need to understand the incredible technology that made it possible. At the heart of this breakthrough is the James Webb Space Telescope, or JWST, a marvel of modern engineering and scientific ambition. Launched in 2021 after decades of planning and development, JWST now orbits nearly 1 million miles from Earth. Its enormous sunshield protects it from the sun's heat and light, allowing the telescope to remain cold and detect the faintest signals from the cosmos, signals that would otherwise be lost in the glare. Its massive gold-coated mirror, spanning over 6 meters, collects light from the most distant and ancient objects in the universe, making JWST the most sensitive infrared observatory ever constructed. One of JWST's most powerful techniques is called transmission spectroscopy. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere, imprinting a unique chemical fingerprint that reveals the planet's secrets. By carefully analyzing this spectrum, scientists can identify the gases present in the atmosphere, even those that exist only in trace amounts, invisible to previous telescopes. Instruments like the near-infrared spectrograph split the faint incoming light into thousands of subtle shades, revealing delicate absorption lines that correspond to specific molecules. This extraordinary precision allows JWST to probe the atmospheres of distant exoplanets with a level of detail never before possible, opening up new frontiers in planetary science. It was this very method that enabled the detection of a potential biosignature on the exoplanet K218b, a discovery that has electrified the scientific community. Thanks to JWST's unmatched stability and sensitivity, humanity has entered a new era in the search for life beyond Earth, with possibilities that were once only imagined now within our reach. The focus of this remarkable discovery is K218b, an exoplanet located about 124 light-years away from Earth, nestled within the constellation Leo. This distant world has captured the imagination of astronomers and space enthusiasts alike, as it offers a tantalizing glimpse into the diversity of planets beyond our solar system. K218b orbits a cool, dim red dwarf star, and was first identified in 2015 by the Kepler Space Telescope during its extended mission. The discovery marked a significant milestone in the ongoing search for potentially habitable exoplanets. What makes K218b especially compelling is its size, measuring about 2.5 times the radius of Earth, and its intriguing position within the star's habitable zone. This is the region around a star where conditions might allow liquid water to exist on a planet's surface, raising the possibility of life as we know it. Earlier observations by the Hubble Space Telescope hinted at the presence of water vapor in K218b's thick atmosphere. However, these findings left many questions unanswered, such as whether vast oceans might lie beneath the clouds, or if the planet's surface is entirely inhospitable. This uncertainty led scientists to propose the Hycean world hypothesis, a new class of exoplanet that could be hot, covered in deep global oceans, and enveloped by a hydrogen-rich atmosphere. Such worlds might be more common than previously thought. The arrival of the James Webb Space Telescope, with its superior sensitivity and advanced instruments, allowed scientists to probe K218b's atmosphere in unprecedented detail, searching for a comprehensive chemical inventory and potential biosignatures. The observing campaign, which spanned several planetary transits, was meticulously designed to detect key molecules in the atmosphere and to rigorously test the planet's potential for habitability. Scientists initially expected to find familiar molecules like methane and carbon dioxide, common markers in planetary atmospheres. But instead, the data revealed something far more intriguing and unexpected. The analysis uncovered a molecule that could fundamentally change our understanding of exoplanetary atmospheres and the potential for life beyond Earth. Once shrouded in mystery, K218b now stands at the very center of the search for life in the universe, inspiring new questions and fueling the quest to find out if we are truly alone. As the JWST team analyzed K218b's spectrum, they confirmed methane, carbon dioxide, and water vapor. But after subtracting known signatures, a faint, statistically significant signal remained. Months of analysis identified the molecule dimethyl sulfide, or DMS. DMS was detected in trace amounts, but the match was clear and confident. On Earth, DMS is almost exclusively produced by life, specifically marine microorganisms. No known geological or chemical process produces DMS in detectable quantities. Its presence is a strong potential biosignature. The discovery, published in Nature Astronomy, is cautious but groundbreaking. The authors stress this is not proof of life, but it is the strongest evidence yet in the search for biology beyond Earth. Detecting DMS in a water-rich, habitable zone planet is a pivotal moment for astrobiology. The implications are profound. Dimethyl sulfide, or DMS, is a simple sulfur compound with the formula CH3-2S. On Earth, it's responsible for the smell of the sea produced by marine microorganisms as they break down organic matter. DMS is a key part of the global sulfur cycle, released from the ocean into the atmosphere. There, it helps form clouds by acting as condensation nuclei. Crucially, over 95% of atmospheric DMS on Earth comes from biological sources. Geological processes produce only trace amounts, and abiotic pathways are inefficient. Finding DMS in K218b's atmosphere suggests a large, continuous source. Just as on Earth, that source could be life. The molecule's presence implies active replenishment, as it would otherwise be destroyed by starlight. This makes DMS a powerful, though not definitive, indicator of biology. The case for DMS as a biosignature is strengthened by the other molecules JWST detected, methane and carbon dioxide. Their presence, alongside a lack of ammonia, fits the profile of a Hycean world, a planet-wide ocean beneath a hydrogen-rich atmosphere. This environment could support life, with water as a solvent and a carbon cycle similar to Earth's. The simultaneous detection of methane and carbon dioxide suggests an active, dynamic atmosphere, possibly maintained by life. On Earth, life keeps our atmosphere in chemical disequilibrium. The same may be true for K218b. The DMS signal fits into this broader, coherent picture of a potentially habitable world. If K218b were dry or a gas giant, DMS would be much harder to explain. Here, the evidence points to a temperate, water-covered planet, exactly where we might expect life to arise. With JWST's data, scientists can refine the Hycean world model for K218b. Hycean planets are larger than Earth, with vast oceans and hydrogen-rich atmospheres. Surface conditions would be hot and pressurized, but water could remain liquid, creating a stable environment for life. The ocean would shield life from stellar radiation, fostering a protected biosphere. The detection of DMS fits perfectly. Microorganisms in the ocean could release DMS, which escapes into the atmosphere. JWST may be sampling the chemical exhalations of a global aquatic ecosystem. K218b is now the first observational candidate for this new class of potentially habitable worlds. The Hycean hypothesis is no longer just theory, it's supported by real data. Extraordinary claims demand extraordinary evidence. Before accepting a biological explanation for DMS, scientists must rule out all plausible non-biological sources. Could unknown chemistry or exotic geology produce DMS on a Hycean planet? Researchers are running simulations to find out. They're also considering volcanic activity, though no known process produces DMS in such quantities. Future JWST observations will aim to confirm the detection and search for other biosignature gases. Only through repeated, rigorous study can the scientific community build confidence in this finding. The process of elimination is underway. The detection of dimethyl sulfide on K218b marks a historic moment in our search for life. For the first time, we have a potential biosignature gas on a world with the right ingredients for habitability. This discovery shifts the search for life from theory to observation. K218b is just the beginning. More worlds await. Science demands verification, and the work to rule out non-biological explanations has only begun. The James Webb Space Telescope has opened a window onto distant worlds, and through it, we glimpse the extraordinary. As we listen to the cosmos, what other secrets might we uncover?